Hello, everyone. Good morning. So I'm going to quote Sasha here and tell you that I hope that you really enjoyed the nice observations that Natasha showed, because I'm not going to show any during my talk, but rather I'm going to motivate and talk a little bit about how is that we model these atmospheres, and also about the origin of these atmospheres, to see if we can actually say something, what we can say about the planet's formation and evolution with these observations. So first of all, I would like to thank the organizers for inviting me to give this talk. I was actually there on the workshop in 2009. I was a grad student back then. You can see me like there. It was funny when I look at this picture again, I started to see many familiar faces. And actually, many of the lecturers and the organizers of this workshop were there, and many of them grad students back then. So I think this is for you a great opportunity to, to learn about these things, but also to meet each other, even for the people online, to see who is working on this, because you will be colleagues and working in the future. So I think this is also a great chance for you for that. Okay, now let's go back to our rocky planets. And I think that's something that we always have to keep in mind when we are doing our research is mainly two things. First of all, to think of why is it that we are doing what we are doing, right? It's not just, plugging in our codes and running things without thinking why it matters. I think it's very important for you to think what motivates you to study these things, to do that research. So here I'm going to give my personal motivations to study rocky planets. I'm pretty sure that many of you will have others, but here go mine. So first of all, I would like to know more about our own planet, about how the Earth was formed, how it evolved. And we have very great, amazing, detailed data on our own planet, but it's one object. And we have a few others in the solar system, and that's it. So exoplanets really give us numbers, give us statistics, give us these things of thinking of very extreme conditions that we haven't thought before. And that might also help us a little bit to understand our own planet as well. On the same note, we also have other rocky planets in our solar system, and they are all very different from each other. Like think on Mercury, Venus, the Earth, Mars. They don't look alike. Even Venus and the Earth have very similar masses, and they are located very similar distances to the sun. They are completely different planets, and we still don't know why. So I think also studying exoplanets puts our solar system in context. Are those planets common in the universe or not? One thing that exoplanets is giving us, and we cannot find that in the solar system, is that here in our solar system, we are observing the planets at a certain evolutionary stage. But when we look at exoplanets, we are looking planets at all different ages. And that also might help us to put, the puzzles together to understand how is that our planets formed and evolve and what happens with their atmospheres. We have a great diversity of different extreme environments, and that also might help us to understand a little bit more about life. So there is a whole other topic that is astrobiology, and people is trying to understand not only if there might be life in other planets, but also how life originated in our own planet. And then studying all these different extreme environments that we are seeing in exoplanets might also give us some other, ideas of where to try to study these things. And the final two are about the lava planets that are some of my favorite rocky planets, and I will be talking about them more during this talk. These are very crazy worlds that are very, very close to their stars. And because of that, they have a surface that is completely molten, and their atmospheres might be made by these vaporized rocks. And the cool thing about these ones is that because their atmospheres are a direct, outgas from the surface, then if we observe these atmospheres, it might tell us something about the composition of that crust. So it's really a direct window to understand the composition of the interior of the planet. And that's why I think they are very cool. And the other thing, and here I'm tuning in with what Natasha was saying, is about the planets that might have no atmospheres at all. I think they are very cool as well, because if you think, when we are thinking of, habitability even, What is coming between us and the people walking on those planets is the atmosphere. But if you have no atmosphere, you can learn about the surface. And we can only do that for those planets. We can learn about geology, exogeology, which is really, really cool. So I think that we also have to start to think about those things, about these planets, and not that they are no results. They are different kind of results, and we need to understand it. All right, so now that I gave you my motivations to study these planets, I think that it's also important to know which are the main questions in the field and which is that we are aiming at. So some of the main questions in this field, I think, first one is that we would like to understand the diversity that we are observing. We have all different kinds of rocky planets out there, and we want to understand them, right? We want to know more about this diversity. How is that we are finding this extreme diversity? And another one, and we were also discussing this during this week, is about the presence or absence of an atmosphere. So we don't know if these planets have an atmosphere or not, especially the ones that we are observing around M dwarfs might be special. Maybe like M dwarfs are very active. The planets that we are observing around them are very close to the star. So maybe all of these makes these planets not have an atmosphere because of the intense interaction with the star. So really, we need to learn more about this. Is it true that they have no atmospheres? And if they do, is it because of the star? If we go to planets around other stars, maybe they do have atmospheres. So we need to know more about this. And I think this is a very important question that we will be tackling with the observations that we have this year. If they have an atmosphere, the next question is, of course, what are these atmospheres made of? And this is not a trivial question at all. It's very difficult to predict which will be the composition of a rocky planet. Think again of the planets in the solar system. And think of the atmospheres of Venus, of the Earth, of Mars, even Titan. The compositions are completely different from each other. So it's very hard to predict what we are going to observe. It's not like giant planets that maybe you can think, well, at least, they were born from the same disk of the star. So we can start thinking like stellar compositions, at least a zero starting point. For these ones, we don't have that. And I'm going to walk you a little bit more about the formation of atmospheres so you understand the complexity of this problem. And the final one is, what can we learn about this, right? We are going to have all these amazing observations. We might observe atmospheres, we might not observe atmospheres, but the bottom line here is that we really want to know what are we learning with those observations, not only to have them, but what are they telling us about the planets, about their interiors, about their formation, their evolution, right? We want to know more about them. So I think that these are my questions about the things that I would like to know more about these rocky exoplanet atmospheres. And now let's go and discuss a little bit more about the formation. Not about the planet formation, that will be, the whole topic for a new talk, but more about what happened with the atmospheres. So the very first stage, it's very at the beginning when there is still gas in that disk. And you have these objects that are growing. You have gas. This gas is hot. It's moving around. It will have certain kinetic energy, but your objects are growing and they have some gravity. So if this gravity overcomes that kinetic energy, they might start accreting some gas. And you don't need to have a giant planet for that. A planet like the Earth can accrete a decent amount of gas in this very stage. But the thing is that, is that planet able to hold on that atmosphere? So this is really the first millions of years of the formation of these planets. But then, of course, we have billions of years more of evolution. And that is really what shapes the atmospheres that we see today. So what happened next, I'm not going to go much into that because we will have a talk about that. But what happens is that these primary atmospheres might be eroded away because of the interaction with the star, because of impacts, because of the energy that the planet still has from the formation. So some planets might hold on that primary atmosphere, especially if they are very big, more kind of super Earths, Neptune-like planets. Some of them might lose it completely. We really don't know. It depends on the history of the planet. And then after that, there is also something that is happening at the same time. So these two processes are really happening at the same time. And is that when the planet is cooling, there are also some gases that are coming from this interior, let's say, although it might be in completely evaporated phase. But then it will give rise to these secondary atmospheres that is really the atmospheres that we are observing today, at least for the planets in the solar system. So you see, they have a very long evolution. And for that reason, it's also very difficult to link with what we are observing with the primordial formation of the planet. But ultimately, and you have to remember this, the things that are, evaporating and will form the final atmosphere depend on those first building blocks that the planet accreted and that put it together. But also, it depends maybe on the impacts. So we are still not sure if the water that we have on Earth was there from the beginning or came from impacts afterwards. So these are also some things that we have to take in mind and not to really rush into conclusions when we are observing some certain gases in these planets. Okay. So which kind of atmospheres we can have? And this is from a review that I wrote with Tim Lichtenberg. It's not published yet. It will be hopefully at some point during this year, but it's more focused really on the interior processes and the formation of the atmospheres. And here are the different types of atmospheres that we identified in this review. And you can see on this side, yes, okay. You can see on this side, these ones here, that are planets that maybe kept some of their primordial hydrogen-dominated atmosphere, but that also might have some secondary volatiles coming up during this evolution. Then we move to the next one, that is more planets that only have secondary atmospheres made by volatiles. And when I say volatiles, I'm referring to gases like water, CO2, nitrogen, and things like that. So for example, the planets in our solar system are in that second category, like secondary volatiles atmospheres. We might have some other cases, and we don't have really examples of those in our solar system, but if the planets are either very close to their stars or they are very hot because they still have some heat from their formation, maybe their surfaces will still be molten. And if that is the case, that magma vaporization will contaminate also the other atmosphere. So then we might have planets that have secondary atmospheres made by volatiles, but also some refractory species like silicates and things like that. And then on the other extreme are the ones that I mentioned before, these lava worlds that are completely made of, they probably lost completely their volatile atmospheres during this evolution, and they only have that very small and tenuous atmosphere that they got due to the outgassing. So during the rest of the talk, I'm going to talk more about these two cases here, just because of time, but I will tell you a little bit about the simulations that are being done to try to understand these planets. Let me start with the lava worlds, and I really like these planets. They are just crazy, crazy things. And let me show you what we think. And again, this is a very big question mark, right? We will see. But this is what we think that happens in these planets. And this is a nice cartoon that one of my students made, but it's based on a paper by Kite et al. That was also trying to understand what happens with these planets. So these are tidally locked planets. They are very close to their stars. So there is only one side that is looking at the star and the other one is not. So one side is going to be very, very hot and the other one is not. So the side that is very hot and looking at the star, that is this one here, it will have a magma ocean, mostly induced because of this extreme irradiation that they receive from the star. And this magma ocean will vaporize and will form an atmosphere mostly made of vaporized rocks. So it's a crazy, crazy idea. We don't have anything like this in our solar system at the moment. Maybe in the past, there was a magma ocean and something like this happening. We don't know. But the thing is that we don't know what happens on the other side of the planet, because the other side is way cooler. And then it might not have a complete magma ocean that will vaporize. So We don't know if this atmosphere is something that might only happen on this side. We don't know if there might be some redistribution of heat. There are like many questions still in these planets that we will figure out with observations. Now, the way that you might say like, well, but these extreme worlds, are there many of them? Well, yes, there are hundreds, which makes them even more puzzling and amazing. So this figure is showing stellar effective temperature and semi-major axis. And here are all the rocky planets. And here we picked the ones with radius less than 2 Earth radii. And all of them have surface temperatures larger than 1,000 Kelvin. So very, very hot planets. And there are hundreds of them. Of course, it doesn't mean that all of them are great for observations, right? Because we learned that the small planets are hard, that you also need to have some combination of the star as well to be able to observe them. But there are a few that could be good targets, and they have names here in this figure. And we actually use these to motivate some of the JWST proposals that now we are analyzing the data. So we will see in the future what happens with these worlds. But let me tell you a little bit more about how is that we model these atmospheres. And the very first stage is to model this outgassing from the surface. So here I'm showing this cartoon of this code that is called LabAtmos that was made by one of my students, Christian Badbuchen. There are other codes as well. There is the MAGMA code by Bruce Fegley that was actually one of the first ones that was used to make these kind of calculations, but the MAGMA code is not open. So LabAtmos and also another one that is called Vapor Rock. I think I wrote it here as well. These two are open source. So if you are interested in modeling these things, you can just play around with them. And what these codes do is basically to calculate this outgassing by calculating the chemical equilibrium between these molten gases and the gases that are going to, not the molten gases, the molten material and the gases that are being outgassed. Of course, this is just the 0-0 step, because after those gases are coming out, we need to know what is happening with them. Are they reacting with each other and forming new species? What happens with the temperature structure in that atmosphere? And of course, ultimately, we want to model the spectra that we might be able to observe. So these are really the steps that are shown here. First one is to calculate the outgassing. And once we have the outgassing, to calculate the chemistry in the atmosphere and the temperature structure. And of course, there is an iteration that needs to be done here because after you have the temperature, that might change your outgassing and so on. So there is an iteration to make this self-consistent. And here I put chemical equilibrium. I would love to do chemical kinetics, but unfortunately, there is not much data. We don't have information on reaction rates. Even some thermodynamic variables are not there. So this is something that we need to work together on if we really want to understand more about these planets. But we will see after we have the observations. We need to figure out if they have atmospheres yet. Okay, so once we have that, we can calculate the emission spectra, and I will show you some of the results that we are getting for these lava planets. Again, this is one example, but there are other papers that are also working on this that I'm showing here. On diverse aspects of observability and chemistry in these planets. So one of the first ones was actually by Laura Scheffer and Bruce Fegley. And here what I'm showing is the emission of 4 exoplanets on this side. And what you see here is actually the contribution to different molecules to this spectrum. So you see, let me just take, well, in all of them, actually, you see these 2 prominent features. One is SiO2 and the other one is SiO. And if you remember what Laura explained the other day about how we can have absorption features if your temperature decreases and how we have emission features if your temperature increases, then this is exactly an example of that. So we have that SiO2 is an absorption feature, and that is because SiO2, if we go to see it here, is in a region of the atmosphere where the temperature is like here. So the temperature is increasing with that. Now, if we look at SiO, that is the other one that is here, is actually dominating in a region of the atmosphere where we have a temperature inversion. And that's why we see SiO in actually emission here. So SiO is really what is causing that inversion. And I'm going to show you also other results next, including volatiles, where we only see these inversions if we have refractories in the atmosphere that are very good absorbers and create those inversions. So if in the future we are actually able to observe these atmospheres, they will tell us something about not only the composition, but also the thermal structure. So they are could be really, really powerful observations. In my last minutes, before, one thing that we also made was to use that feature to actually see which planets could be good targets for follow-up observations. Particularly, we use MIRI in that calculation. I'm going to skip that because of time, but I'm interested if you are interested, we can talk about that. Let me just move to the other category that I wanted to mention, that are planets that might have magma oceans on their surfaces, but they also might have a secondary atmosphere made by volatiles. So maybe they didn't lose all the volatiles yet. And here are also some papers that are dealing with this. I'm going particularly to show the results of Angeli Pitt, that she published a paper this year, and also my student Pantas, that they were also on the same topic, but they use different kinds of atmospheres. So it's interesting because they are complementary. So this is more or less what these planets would look like. And they are a little bit different than the one I showed before, because in this case that they have a volatile atmosphere on top, these atmospheres might be thicker, and then there might be some redistribution of heat going on, and the atmosphere is not only on one side. So they might have a different geometry as well as the one that I showed before. Now, the question is, of course, which volatile species they might have. And in this paper, what we did was to put on top of that magma ocean an atmosphere dominated like a primary atmosphere, mainly of solar composition. And what Angeli did in her paper is more to use water and CO2 and oxygen on top of that mantle. So the idea, I think, of both papers is to see if we can see any tracers of that magma underneath that is contaminating the atmosphere. Because again, we want to know what are we going to learn from these planets. And if we observe some silicates, that probably will tell us that there is some surface that is molten and is being contaminating that atmosphere. And if we observe that, we will be able to say something about that composition. So it's also very interesting if we can actually observe these silicates in the atmospheres. But they are not so easy. So the spoiler is that they are not so easy to be observed, because as soon as you put, a volatile atmosphere on top, most of the features that you are going to see are going to be of any gas that you put on top. If you put water, you are going to see water. If you put CO2, you are going to see CO2. So, so only in the cases of very extreme temperatures, very extreme outgassing, then in those cases, we see in this case, these SiO features. We also find titanium oxide. And here, let me show you the results by Angeli. She did something similar. So there are these three cases. This is actually 55 Cancri E that she's modeling. And you can see the different vapor fractions. So it's a similar way of studying this. So she tested which are the different outgassing and which would be the outgassing that you need in order to see these features. And it's also the very extreme case. So we are actually finding very similar results with different studies. Another thing that these two studies also have in common is a temperature profile. So what we see in both cases, it doesn't matter if you put this atmosphere or if you put a solar composition atmosphere. What we are observing is that the atmospheres only present these inversions in the case of extreme outgassing. So these silicates are the ones that are causing these inversions in these atmospheres. All right, so let me wrap up here, and I hope that you have many, many questions. And first thing that I want to bring you is that the atmospheres of these planets is a very complex process, the one that ends up with the nice atmosphere that we have here today. But we want to know more about it. We want to know what happened with these planets, and they have each one of them a unique history, a unique evolution, a unique formation. And we want to know how that happened and if that is the same or different than the ones in our solar system. Remember in that scheme that I showed of the different types of atmospheres, well, we need to start putting some names there of different planets that belong to each one of those categories and see if we can learn something about that process. And another thing, particularly of these lava planets that I wanted to mention because they were not discussed this week, they are very interesting planets because they can give us really direct information on the interior. I really hope that we can see something in those spectra. It remains to be seen. And planets that also have volatile atmospheres, they might have inversions. So we might learn not only about the composition of the atmospheres, the composition of the mantles, but also about the thermal structure of the planet. And one last thing, if you want to know more, go and check, but Natasha already told you there is this very nice review by Laura and I forgot the name. Robin, thank you. Robin Wordsworth. And we are also writing this one. Well, it's written already with Tim that is complementary because his focus is more on the interior processes and formation of atmospheres that will be hopefully soon out there. Last comment on my side is that in my group, we don't only do rocky planets, we also work with giant planets, exoplanets, and also solar system planets. And right now I'm hiring postdocs. So if any of you is graduating soon and is interested in working in interiors and atmospheres, particularly the connections between interiors and atmospheres of giant exoplanets, come and talk to me. And thank you for your attention. Thank you.
Thank you for the great talk, Yamila. So how is the outgassing that you're seeing this level was compared to outgassing that we see in a solar system object like Io?
So Io has not a completely magma ocean, but it's more localized volcanism. And it's also caused because of the tidal interactions with Jupiter. So it's not that this, heated from above and that gives it the magma ocean. It's more heated from inside the planet and that creates that volcanism. So then we don't have like a complete atmosphere made of that, but more some, gases that are being erupted. They kind of are bounded and you can think of them as an atmosphere, but it's a very, very tenuous one. While these ones, if you have very high temperatures, you can build up like a quite decent atmosphere of, let's say, 0.1 bars, even 1 bar if you have a 3000 Kelvin planet. Yeah.
Thanks so much for the great talk. This is Katie Bennett from Johns Hopkins University. So I have kind of a naive question in that I'm wondering if you see SiO2 in an emission spectrum, how do you tell the difference between whether that's something that, like you're seeing an atmospheric feature that has been outgassed from a magma ocean versus seeing actually down to the surface and seeing like silicate rocks on the surface?
So if you are seeing the surface itself, the features are a little bit different than the ones of the gas. So I think that could be mostly the main thing. But I'm not quite sure if there are many studies of reflected light from surfaces with silicates. I have to look into that.
Yeah. So this online question asks, is it possible to predict the age of the planet from the outgassed atmospheric compositions that we get from the modeled or observed transmission and emission spectra?
Yeah, that's a great question. So the problem is that we don't know very well which is the composition of that mantle to start with. But it's true that with time, there will be some gases that are going to be evaporated first than others, and then they will be depleted from that mantle. So then the atmosphere that you will be outgassing with time changes. So in a sense, it could be possible. We tried that actually in the paper, but there is not a huge change in the features that we are observing.
Thanks for a great talk. Can you say a little bit about how you expect this equilibrium chemistry to change results, and if at all, given that you have very high temperatures in the atmosphere?
Yeah, so even though they are very hot planets, I think photochemistry might be something to think about because they are very close to their stars. So maybe there is some photochemistry happening there that might destroy even those nice silicate oxide features that we are seeing, but we don't know. There is a nice paper by Yuichi Ito starting to think on photochemistry in these planets. There is still a lot to be done, but I think that would be the main effect.